let's take a look at Euler's formula. Euler's formula says that e to the I theta equals cosine theta plus I sine theta. So this is something that we are given, and we want to apply it in order to make a new form for a complex number. So taking what we know so far, we can now come up with a polar form of a complex number. So z equals x plus yi was just our regular rectangular form. That's what we're introduced to in terms of complex numbers. And then we said, well, because of what we know with polar coordinates, and we said, x is our cosine theta, and y can be thought of as our sine theta because of the location of x plus yi as the complex number corresponding to x comma y, the point in the plane. And then we said, okay, taking out the r, just factoring that out gives us the trigonometric form, and that seems good, okay? And then we said, well, I recognize this cosine theta plus I sine theta in Euler's formula up here. And what we can say is that cosine theta plus I sine theta is equal to this e to the I theta. So what I do is just replace the cosine theta plus I sine theta in my trigonometric form with e to the I theta using Euler's formula. And then when I do that, I get the polar form here of a complex number, which is just r times e to the I theta. So it still has the r and theta information, but it's just a little bit more compact. It also makes some operations on this type of number a little bit easier, as we'll see when we look at like square roots or cube roots of complex numbers. So let's complete the table knowing what we know now. So some of these things we found previously. So what I'm going to do for those first three rows is just go back up. Try not to get too seasick here. So I had 3 root 2 and 3 pi over 4 for this first one. So I said this was just z equals 3 root 2 cosine 3 pi over 4 plus I sine of 3 pi over 4. So this is us just kind of getting our table ready. What did we have for that second one? We said this was root 5 and 1.12 for the angle. So z is root 5 times the quantity cosine of 1.12 plus I sine of 1.12. And then going back this other way, I think we had z equals -1 plus root 3i, because cosine of 2 pi over 3 is -1/2 times that too. Yeah, that looks good. Okay, and then I did add this fourth row here to kind of check that out. Okay, so let's say, what would this polar form of the complex number be? Well, all we really need to do when we have the trigonometric form is just identify the r and the theta. So here r is 3 root 2, and the theta is 3 pi over 4. And I can just tell from where they are in the formula. And so then to write the polar form, I just have z equals 3 root 2 for the r times e. And this e is the same as the base of the natural log. So that's e that you've seen before. I, and then the theta is just 3 pi over 4. So I just write it like that. All right, let's do it for the second one. So z equals r is just root 5. E to the I, and this angle was one that we had to kind of approximate 1.12 radians. And we do need to be in radians here, so just make sure that that's the case. Okay, so from here, r is 2, theta is 2 pi over 3. So z is 2 times e to the I, 2 pi over 3. All right, so in the fourth row, we are given the polar form, and we need to go this way to the trigonometric form. So I just need to identify r is 3, theta is pi over 2. So z is then 3 times the quantity cosine of pi over 2 plus I sine of pi over 2. Now this feels a little weird to leave it like that because it feels like you should evaluate and keep going, but that is what the trigonometric form of a complex number looks like. So we want to leave it like that. Okay, but then to go to the rectangular form, we definitely want to evaluate it. So this would give me 3 times cosine of pi over 2, let's see, that's 0, plus I sine of pi over 2 is 1. Multiplying that in, we get 0 plus 3i, or just 3i.